Okay, we started the recording. I'll start the backup also. Okay. So in the previous week, we were discussing the chapter on buckling of columns. And because we had the test on Wednesday, we were not able to discuss it fully within the scope of that week. In terms of the actual theoretical discussions, I just have a little bit left. So I'll complete that in this class itself. Uh, now, uh, I told you that I would be recording something. I haven't done that yet because I was busy preparing the tutorial sheet corresponding to buckling. I have done that and I have also uploaded that uh, in our course website. It is available as TS9. Um, what I will suggest is that uh, there are basically 10 problems there in the tutorial sheet, and uh, in terms of the difficulty, it is not that high. Okay, so and there are not too many problems. There are 10 problems. 2 of them are derivation based. There are basically 8 problems, so to speak. Now, I've tried as much as possible to grade those problems in terms of difficulty. Like question 1 is kind of the easiest, and then you proceed along. So I suggest you try out a few problems there and we can have a discussion. And if I find some time, I'll try to make a recording of a few problem solving as I do it, like as I discuss it in class. However, in this class, in the first 10-15 minutes, I'll just quickly discuss the remaining theoretical portion of buckling of columns. Is a very easy thing, but it's an extremely important thing as far as problem solving is concerned. So let's get into that, and immediately after that, I'll start with the last chapter of our semester, which is energy methods. So that is the plan for today. Okay, so this particular case where the column is clamped at both the ends, I have now made this part of tutorial sheet number 9. In fact, this is the question number 10. Okay, so and I have guided you in that problem statement how to go about doing it. In case there is any issue, I'll just provide you the solution. Okay, it's not that difficult. Let me just discuss the actual theoretical part. Now, we have seen a number of cases. Okay, so including the previous one, this one, we have seen this. There are 4 cases. There could be other more involved cases also, but these are like the elementary cases of buckling of columns. Now, in each of these, you will notice that the critical load that can be expressed as this kind of a formula: pi square EI by L effective square. So if you have a pinned end, which was our case number 1, then L effective was equal to L, and then you may have 0.5 L, you can have twice L and other things. Okay, so sometimes this is also written as pi square EI divided by K L whole square, where K is the factor associated with the particular boundary conditions. For different boundary conditions, we'll have different K. There's different ways of writing the same thing, okay? Because in different books and different places, they mention these kinds of things. I thought that I'll make you familiar with it. However, the more important thing to note here is that suppose we go back to our case number 1. Okay, go back to our case number 1. If we discuss the thing which I want to discuss with respect to that case, you can do a absolutely similar thing for the other cases also. So we had the pinned case here, and there the P critical was equal to pi square EI by L square. Now, what we can do is, at the critical point where it is buckling, when you have this P critical force, we can take or we can divide this thing by the area of the column, by the area of the cross section of the column. So if we do that, this thing becomes the critical stress, and that is equal to pi square EI by L square A. Now this thing, this expression, it can be somewhat recast in a different form by noting that the second moment of area, okay, the second moment of area or the moment of inertia, it can be expressed in a very general way, like the area times the radius of gyration square. Okay, so this is the radius of gyration. I believe you have come across this word gyration back in your +2 when you were studying physics. Back then it was something like mr square in the context of the actual moment of inertia. And here it's the same kind of concept. Okay, so around the axis of concern, there would be a certain radius where you can consider the entire area to be concentrated. Back in +2, it was the entire mass that was concentrated at that radius. Here is the entire area is concentrated at the radius. Okay. Please also note that we know for a rectangular cross section like this is B and this is H. We know that this is 1/12 BH cube. So the dimensions of this is dimension of I is meter to the power 4. Please also note that this is dimensionally matching with that because area is meter square, r square is meter square, together it is meter to the power 4. All right, now if we substitute this thing back here, then sigma critical, the critical stress, it becomes pi square E A r square divided by L square A. This A cancels with this A. We are left with pi square E r square by L square. And this can be further rearranged to make it look like this, L by r square. Now this L by r, this is referred to as the slenderness ratio. And in the design of columns, this slenderness ratio plays an extremely important role. Why is that? Let's do one thing. Let us try to plot this sigma critical versus this L by R. Okay, so it's going to look something like this. On the x-axis, we have L by R, not L by R square, okay, L by R. And here we have the sigma, okay, the sigma critical. So for different values of L by R, as long as we are looking at the same kind of material, because please note that the sigma critical also depends on the Young's modulus. Okay, pi is just a constant. So as long as we are looking at the same kind of material, this is kind of inversely proportional to the square of the slenderness ratio. So this plot will look somewhat like this. Okay, very rough kind of plot, but I just want to get you to feel, get a feel for this kind of thing. However, there is a little bit of an issue here. You see, when the L by R ratio, the slenderness ratio, it becomes quite small, then this sigma critical value becomes quite large. Okay, as you can see, it is inversely proportional to the square of the L by R. So this is increasing quite fast as you decrease L by R. Now, this is a little bit of a problem because all of these things are being considered from the point of view of buckling. But when you are designing a mechanical system, nobody is going to tell you that, okay, you just be concerned with chapter number 9 or chapter number 10 of mechanics of solids. It is not like that. Okay, so everything and anything which is of concern, you must be concerned with. That is your responsibility as a professional engineer. So can you tell me what are the things as an engineer, we must be careful about when we see that some critical value of the stress is increasing so significantly? What are the things we should be careful about? You have done many problems where various kinds of limiting values of stresses are given. In many problems you have encountered this, right? Sigma allowable, sigma ultimate, factor of safety, this, that, sigma yield and whatnot. So in this kind of a situation, what is said is that, okay, we have these different values of the critical stresses corresponding to buckling. But when it is increasing like this, there may come a time, or there may come at a point where this sigma critical becomes equal to the yield stress, okay, becomes equal to the yield stress of the material. That can happen something like this. So if your sigma yield is something like this, sigma yield, then you draw a horizontal line here, then beyond this point, okay, if you lower your L by R value beyond this value, okay, if you decrease it below this, then your sigma critical is going to become larger than sigma yield. So the thing that you have to conclude is that this particular region of the curve is not really of concern here. Okay, we should not be, I mean, it's all right from a mathematical point of view to extend it like this, but from a design perspective, it does not make any sense to go into this region. Okay, so if our L by R value is so small that sigma critical is greater than sigma yield, it is actually the yielding of the material which you should be concerned with. So there is a competition between the yielding of the material and the buckling of the material. And these kinds of competitive influences you must be extremely aware of in a real professional engineering situation. That is why in each of the problems that have been given in the tutorial sheet, the expectation is that you will find out the values of the P critical. That is not a very big deal. Okay, when you do the problems, you will realize, I mean, it's not such a big deal to find out the P critical as long as you are a little bit careful about the boundary conditions. But when you find out the P critical, please also make sure that you are not in that process exceeding the yield stress of the material. You know, I mean, for example, structural steel. Okay, so such structural steel will have a value of the yield stress something like 250 MPa. Okay, for steel. Different grades of steel will have different. This is structural steel. Okay, very common kind of steel, something like maybe A992 steel or something like that. So we need to be careful about this thing. Okay, another aspect which you should be careful is, you see, again, let us consider this P critical associated with the case 1. We have seen that P critical is equal to pi square EI by L square. You focus your attention on this I. Okay, you focus your attention on this I and you consider the column properly like this. Okay, your column is like this. Suppose it has a rectangular cross section. Something like that. And at the top end and the bottom end, it is pinned. Okay, so pin joints are there. So you understand. Okay, so I'm just drawing it very roughly. So we have this pin joint here. Now, if we focus on this cross section, okay, this is a rectangular cross section. And let me also try to maybe set up an axis. So we had taken earlier our x-axis to be pointing downward. So this is x. This is our, let's say, y, and this is z. Okay. Now, this is our rectangular cross section. This is B and this is H. So now you see, we can find out the I. Okay, we can find out the I corresponding to this one. Okay, So something like this. We can find out the I corresponding to this one. So this I is equal to 1 by 12 BH cube. But we could easily also find out the I corresponding to this one. Okay, so that I will be 1 by 12 HB cube. Both of them are the second moments of area, just calculated about two different axes. So this orange one, that orange one is the Z axis. You can think of it like that. And this yellow one, that is like the Y axis. Whose value is higher, do you think?
So the orange one.
Orange one has a higher value. Okay, so this thing I, let's call this what? IZ. Okay, and let's call this one as IY. So this IZ, it is greater than this IY. Or IY is less than IZ. Now, this is the same mechanical system which has two possibilities of, or two possible values of P-critical depending on which one you take, IZ or IY. If you take IZ, you will get a certain value of P-critical. If you take IY, you will get another value of P-critical. Because length is length, Young's modulus is just of the material, pi is a constant. So P-critical depends crucially on which value of the I you are taking, IZ or IY. So definitely if you take IY, your P critical will be smaller than the case if you take IZ. So which one should you be considering for critical conditions?
So we should be considering IY.
Very good. Okay, so for actual P critical, consider the I minimum. This is very, very important. Okay. Okay, because you see this column will have a tendency to buckle like that, or it will have a tendency to buckle like that. But actually, given a certain load, there will be a bigger tendency for it to buckle about this y-axis. Okay, or in this or in the XZ plane. Okay, so please be careful about this thing. These are very, very small things. I mean, there is no calculus or anything involved here, no differentiation, integration, simple algebra, but crucially important for the design of such columns. And in the problems, you will face certain situations where you'll have to be careful about this. So I just wanted to point it out. All right, that's all there is to it actually. Let us now go to the energy methods chapter, which is our last chapter of this mechanics of solids course. Okay, so energy methods. So my first question as we begin a new chapter is that have you actually come across energy methods previously? Okay, previously means you may not have come across in your first year, certainly not in first year mechanics, basic engineering mechanics, but I'm asking about +2. All of you are masters in your course contents of +2, especially maths, physics, maybe not so much in chemistry, but certainly in maths and physics. So tell me, have you come across these things in physics, energy methods, while solving problems in mechanics?
So do you mean
Yes, sir.
conservation of energy?
While dealing with?
Do you mean conservation of energy?
During conservation of energy, yes, very good. During conservation of energy. So point is this, okay, when you are trying to solve mechanics problems, there are two different styles of doing mechanics problems. One is what is usually referred to as the Newtonian approach, where you draw the free body diagram, draw the forces and everything, take a balance of the forces, take a balance of the moments and all these things which you have been doing all along since your, which is by far the most common thing that you do. However, in +2 physics, you were also exposed to another way of doing certain problems, which became much more easier to tackle using the energy methods. In +2, you used conservation of energy. Now, I believe that as you are doing your your other course of dynamics, you must have encountered certain problems where you have to be extra careful while using energy methods. Okay, what I mean to say is that certain kinds of problems which seem that will work like with using conservation of energy, they don't quite work with conservation of energy. So I think Professor Dasgupta or Professor Sarkar must have given you certain problems involving chain links, chains, some mass is connected to a chain lying on a table or hanging from a pulley or something like that. And the initial temptation is to use conservation of energy. But if you do that for problems involving chains, it will go wrong. Okay, because the chain links, they themselves have friction, so energy is not conserved. So you'll actually have to do, calculate the work done, and then only you can solve those problems. Now, the point that I want to illustrate here is that there is a separate way of dealing with certain problems involving mechanics in general, whether it is statics or dynamics or mechanics of solids. If you appeal to these kinds of energy methods, there is a separate, entirely separate way of dealing with these problems. Now, question is that you have been doing all fine. Okay, you have been able to solve various kinds of problems using these Newtonian mechanics, like drawing the free body diagram and all these things you have been able to do. What is really the motivation of studying these energy methods? I mean, as an intellectual exercise, it is fine, but why complicate life like this by trying to study another method? What is the real motivation behind this? Can anyone guess? I mean, intellectual pursuit and increase of knowledge, these are all good arguments, but I'm asking in a very business-like fashion. Okay, is there any real benefit of learning these energy methods, do you think?
So initially while learning it would be an additional method, but while solving some problems, it would be a better way to get to the answer. So for suppose if we have some forces which are conservative or non-conservative, and we need the problem to be solved using the initial and final stages, then we can use these kind of energy methods and make a problem solving a bit easier.
Yes. Okay, the key word which I want to highlight here is that certain problems are such that if we use energy methods, they actually become easier to solve. Okay, they actually become easier to solve, much easier. Okay, for example, the deflection of beam problem, that cantilever beam problem. You have learned how to do it, how to solve it by solving the deflection equation, the second order differential equation. But let me tell you, any one of us who has studied energy methods, if we forget the formula sometimes and we don't have our textbook handy or internet handy with us, and we have to derive it, we don't do it by deflection. Okay, we use energy methods. Okay, this is a little trade secret I'm sharing with you. So certain kinds of problems are such that they become much easier. Like it almost feels like cheating when you are using energy methods to solve those kinds of problems. Of course, it is not cheating because there is something called the conservation of difficulty in life. Okay, in order to gain something, you have to lose something. Okay, so the thing which you have to lose is that it's not actually losing, but the conservation of difficulty plays out in the fashion that the theory behind these energy methods is a little bit more involved. Okay, you have to start orienting your brain in a slightly different way. Okay, it's very exciting and fun to learn it, but until you have learned it, it is uh, it is a stress on your intellectual efforts. Okay, you will see that. Over and above that, there are some other motivations also, and let me tell you that which I do not expect any one of you to know at this point, which is why I'm telling you. A big motivation is that these energy methods, uh, they are like the very first basic steps towards the development of certain kinds of numerical methods, which some of you may have heard about, something like finite element methods or finite volume methods. So these are the kind of methods of solving very hard differential equations which arise in the solution of professional level engineering problems. Okay, professional level engineering problems which cannot be solved by these kinds of tutorial sheet level maths. Okay, you have to solve very hard differential equations, very non-linear, coupled, very difficult boundary conditions, very difficult geometry, so real world problems. So those kinds of things have to be solved using methods like the finite element methods. Some of you may have joined certain societies, and maybe your seniors have encouraged you to learning a software or something like that, and maybe you have run those things, and maybe you know the buzzword finite element methods or something. But let me tell you, this chapter, it is what provides you the absolute basis of it. Now, please do not fall under the misunderstanding that the moment you finish this chapter, you will automatically understand finite element methods. In fact, you won't even realize the connection between energy methods and finite element methods until much later. Okay, but you'll have to wait a couple of years to gain that full all-round understanding. So this is my promise to you, that learn this thing. It will later connect on to bigger and better things. Okay. Another thing is that Newtonian mechanics way of solving problems is fine, but this energy methods, it provides us a method of solving mechanics problems in a style which is which has a certain commonality with other areas of physics. For example, optics. For example, electromagnetism. Even quantum mechanics. So these, like the spirit behind these energy methods, okay, the philosophy behind these energy methods is so very common and general that once you understand, like really understand the heart and soul of it, the essence of it, you can actually understand without much difficulty the way of solving quite a few different problems in optics and electromagnetism and such other things. Now, why is that important? Why, as a mechanical engineer, would you be interested in those kinds of problems? Because, as I told you, when you go into the professional level, whether it is industry, when I say industry, I mean core industry, or you go into some kind of research lab, or you go for higher studies, the problems that you are going to be tackling, they are not just going to be limited to only one, certainly not going to be one chapter of mechanics of solids or elasticity or fluid mechanics or anything like that. Rather, they will be, covering different kinds of subjects within mechanical engineering, and many a time, some subjects which are not traditionally part of mechanical engineering, like optics, like electromagnetism, okay, sometimes even quantum mechanics. So it makes sense for us as modern day 21st century engineers to really get to the bottom of these kinds of general methods which will provide a unified way of solving problems. Okay. Furthermore, within the context of mechanical engineering, these energy methods are also the basis of higher level courses. Like when I say higher level, I don't mean third or fourth year level courses. Okay, I mean advanced level courses, even from the point of view of PhD students. Okay, so they get to study certain, or they need to study certain subjects, especially if they are working in the domain of solid mechanics or fluid mechanics. They will eventually have to study subjects, one subject called continuum mechanics and thermodynamics. So continuum mechanics is a very mathematical, very formal way of tackling the underlying theory behind solid mechanics and fluid mechanics, which falls under the umbrella of continuum mechanics. But continuum mechanics cannot work in isolation. It has to always go hand in hand with thermodynamics. Okay, so continuum mechanics plus thermodynamics is what will cover the underlying theory of the kinds of general problems that are needed to be solved within solid mechanics and fluid mechanics. And these kinds of energy methods, when you get to that level, like if you ever get to that level, you will realize what is going on. Okay, why we taught this at the second year level. So with this very general and broad strokes kinds of discussions, let me go forward and actually start the discussion, which will be relevant for solving problems at this level. Okay, and the promise is that for certain kinds of problems, you will see that energy methods provides a much easier, much faster way of solving certain problems. Okay, all right. So the first thing that we are going to discuss is something called strain energy. Okay, strain energy. Now, I believe that people who have studied in CBSE board, they must have come across this phrase strain energy somewhere in their studies of physics in +2. Am I wrong? Please tell me. I'm not going to ask you, okay? I will not ask you for the definition. Without any hesitation, without any fear, you can tell me just yes or no. Have you come across the word?
Yes, sir.
Okay.
Yes,
So that is fine.
Yes, sir, we have.
Okay. What about other boards?
Yes, sir. Even some state boards also have this thing.
Okay. Yeah. So I remember in my state board, it was there, but that was like 20 years ago. What about in South India? Because I really don't know about the state boards of South
I'm
India.
from South India, and it was me who said that.
Oh, great. What about Maharashtra, Madhya Pradesh, all these things? Was it there?
Yes, sir. It was there in Maharashtra board also.
I'm talking about state board, okay? I'm not talking about CBSE because CBSE is same all throughout India.
No, sir. I'm talking about state board of Maharashtra.
Okay. I grew up in my schooling was in Assam, so I know for a fact that in Northeast India it is there, and I'm sure in West Bengal also it is there. Any kid from West Bengal? Any student from West Bengal? Okay, West Bengal board, okay, not like Kolkata CBSE school. Not a single guy from West Bengal State Board. Right. Okay. Anyway, so we have this thing called strain energy. Now, when this is introduced in +2, it is certain. I mean, it is introduced in such a fashion which makes the understanding kind of easy. But I want to present it to you in a slightly more general way. Okay, general way doesn't mean that I'm going to present advanced things to you. I'm going to present it to you using things which you have already studied, which you have some idea about. And the way that I'm going to do it is by starting out with the first law of thermodynamics. Okay, so first law of thermodynamics, tell me what is it? Now I know that the students of manufacturing and QDM, they will be at a certain advantage because they are doing thermofluid science, and they have, I mean, it is very fresh in their mind. So if possible, please don't say, okay, you guys, MF and QDM, the ME guys who have not yet, who may not have revised it very recently, maybe except in chemistry of first year. Tell me what is the first law of thermodynamics? What is the statement? General way, okay? Don't tell me formulas or anything. This general statement, tell me. And don't tell me for a cyclic process because I mean, Tell me for a non-cyclic process. Again, don't be afraid. Nobody is going to cut marks. Okay, just tell me whatever you remember.
The total energy will be constant, like the internal energy change, the external work done, or the heat supplied. So it would be like constant for the whole process.
It will be constant. Okay, so you have hit some correct words. Work done, internal energy. Those things are definitely involved in first law of thermodynamics. Can somebody maybe organize that thought a little bit more and tell me?
So the part of the heat supplied is converted into internal energy, and the rest of the heat energy is converted as work done.
Okay, so work done is there, heat transferred is also there. Very good. Okay, so we are supplying some kind of, we are inputting. So if you're considering a mechanical system undergoing a process, okay, and don't even bother about thinking about a reversible, irreversible process, all those things. Okay, just a straightforward normal process. Whether it is reversible, irreversible, at this point we don't care. So we are doing some work into it. So we are inputting some kind of energy into it, and then we are inputting some kind of heat also into it. Okay, and in the process, what happens? When you are inputting energy into a mechanical system, its energy is increasing. Okay, definitely it's increasing. Okay, you're doing work onto it, you are putting heat into it. Definitely energy is increasing. So one of you just said that the internal energy must increase. Anything else that should increase possibly?
Sir, entropy.
कुछ भी entropy ठीक है increase होगा, but in the context of first law of thermodynamics, how is entropy coming?
So like if we change energy, then the randomness will increase.
No, I'm not saying entropy is not going to increase. Entropy is going to increase fine, but in the context of thermodynamics, we don't write. We don't include the entropy thing, right? I'm just saying that if you are adding up the work done on the mechanical system together with the heat that is input into it, it increases the internal energy. Okay, delta U is depicting the internal energy. Does anything else increase along with it?
So basically internal energy would be the function of temperature.
That is fine. You know this thing. This is the thing actually which you have learned in your plus 2. You have forgotten that and you are telling me high level things.
Potential energy.
Potential energy is within this thing, calculated within this part only. Okay, internal energy.
Volume, pressure, etc. things.
Are Baba. You consider like a simple spring mass system. If you do work on it, what increases for the mass? Does it start moving? The mass start moving or not? If you do work on it, then start moving means what?
Kinetic energy.
Okay, so probably when you studied in your plus 2, you studied it in the form that work done plus heat is equal to increase in the total energy, and the total energy was perhaps written as increase in kinetic energy plus increase in potential energy. But this is a slightly more general form where we write this as the increase in the kinetic energy plus increase in the internal energy. That's it. Okay, and when you study thermodynamics, flow processes and whatnot, you will learn more sophisticated versions of this. You will also learn expressions or equations involving cyclic process. All that when you study thermodynamics, your thermodynamics teacher will tell you, we are concerned about simple mechanical systems. So I will tell you what we need to know. Okay, now we are going to simplify this equation, first law of thermodynamics, because let us not forget, we want to apply this first law of thermodynamics on what kind of problems? Problems involving beams, problems involving shafts, then maybe some problems involving some kind of springs or something like that. Okay, these are the kinds of things which we are concerned with within the context of mechanics of solids. Okay, we don't need piston and fluid and gas pressure and all those things. Okay, now most of the problems that we will be dealing with, they will be undergoing processes which are adiabatic in nature. What is the meaning of adiabatic?
Heat exchange is zero.
Q is equals to 0.
Total exchange equal to 0.
Okay, adiabatic means Q equal to 0. Okay, Q equal to 0 means neither heat is being input into the system nor is it coming out of the system. Okay, so Q equal to 0. So this goes. Furthermore, we are going to consider cases which are quasi-static. Quasi-static means they are undergoing changes in their configuration in a very, very slow fashion. Okay, so for all intents and purposes, they are in static equilibrium. Static equilibrium means what?
Delta K equal to 0.
Very good. Delta K equal to 0. So we are left with W is equal to delta U under the conditions that the process is adiabatic and all the work done and everything, all the changes are taking place in a quasi-static fashion. So work done on the mechanical system as it undergoes a process will result in the change or in the increase of the internal energy. Okay. All right. Now we are going to connect this strain energy to this internal energy. How? Let's go to the next page. We are going to now consider mechanical system. Okay. Now, special kind of mechanical system which we are going to refer to as elastic. Okay. So a mechanical system is said to be elastic if the internal forces are conservative in nature. When you go to higher classes, you will learn. Higher classes means you don't have to go to PhD level. Okay, so suppose you take a course like Advanced Mechanics of Solids, maybe you can take that in your 4th year, and for dual degree students maybe 5th year. You will learn things like these internal forces are conservative. So conservative can be in two senses, static and kinetic sense, but right now you don't have to bother about all those things. Okay, but the formal definition is that a mechanical system is said to be elastic if the internal forces are conservative in the kinetic sense. Okay, so leave that out for now. What we want to be concerned with is that internal forces are conservative. This is the main thing. So if someone asks you what is the general definition of an elastic mechanical system, this is the thing. Okay, don't say that it should follow Hooke's law and those things. Those are just cosmetic things. Okay, very special case kind of things. Those are not the most general thing. This is the general thing, that the internal forces are conservative. Then it is said to be an elastic system. That's it. Now, you have already learned in your +2 that if forces are conservative in nature, okay, so if forces are conservative, then some kind of potential will be associated with it, or we can say some kind of potential energy will be associated with it. If the forces are not conservative, then you can't associate a potential energy associated with it. I mean, you cannot associate any potential energy with it. Okay, then some kind of potential energy will be associated with it. All right. Okay, so just like gravitational forces, so you will have some kind of gravitational potential associated with it. Okay, so similarly, the electric potential. Okay, so those kinds of things happen only because the forces are conservative in nature. All right, this is the general idea which you all know. Now we have already seen that our elastic system will have internal forces as conservative, which means that with this, if you connect it with this general idea that if forces are conservative, some kind of potential energy must be associated with it, which means that elastic systems, the internal forces that are present within that elastic system, because they are conservative in nature, therefore the internal forces or you can say the conservative internal forces, just to be very explicit about it, the conservative internal forces in an elastic mechanical system must also have a potential energy associated with it or with them. Sorry about my bad handwriting. Okay. Must also have a potential energy associated. Okay. Now this thing, okay, this potential energy associated with the conservative internal forces of an elastic system, that is what is referred to as the strain energy. That's all there is to it. Okay. So first of all, we understand that a mechanical system is elastic if the internal forces are conservative in nature. We understand that if forces are conservative, then there must be potential energy associated with it. So the conservative internal forces in an elastic mechanical system must also have a potential energy associated with it. And it is that potential energy associated with the conservative internal forces in an elastic mechanical system which is referred to as the strain energy. Finished. Okay, this is our strain energy. So I have not written a single equation expression. Sorry? Sorry, say that again.
Sir, I think someone got mistakenly unmuted.
Okay. Let me just check. If someone got mistakenly admitted, either you leave or you just sit quietly and listen to the great ideas that we are discussing. All right. So you understand this strain energy business. So we now got to express this thing properly. All right. So how do we go about doing it? Any ideas? Okay.
As you said previously that we'll be considering some finite mass elements. So in case of deformation and deflection, we'll be considering the force, the work done on that because of the external force applied, and we also consider the deflections.
Yeah, but see, I have not yet made the connection with this expression. Like, why the hell was I discussing all this? W is equal to delta U. Just for fun was I discussing, or what? What is the thing? Okay, so what I want to say here now is that this internal energy, W is equal to delta U, I want to connect this idea with this idea of the strain energy. And that's a very simple thing to say. Of course, I won't go into the intricate details within it. So something that you have to accept on good faith is that this strain energy, okay, strain energy means basically the potential energy. So the strain energy differs from the internal energy only by an additive constant. I think it's better if I take this thing next page. All right. The strain energy differs from the internal energy only by an additive constant. What is the implication of this? Implication is simple. Earlier we have seen that W is equal to delta U. That is the work done on a mechanical system as it undergoes any general process results in an increase in the internal energy of the mechanical system. But here we are saying that the strain energy differs from the internal energy only by an additive constant. So let's say that the strain energy is given by something called delta, I don't know, maybe some delta U bar. Okay. Now this delta U bar will be perfectly equal to the delta U. Why? Because the only difference between U bar and U is some kind of constant. So you can think of it like this, that U bar is equal to U plus C. And this is just an additive constant. Okay, so delta U bar will be equal to delta U because delta C is equal to 0. All right, so now what we are going to interpret this equation, earlier we had interpreted it as W or work done results in a change in the internal energy of the mechanical system. Now we are going to interpret it like change in the internal energy, change in the strain energy. All right, so now we have a certain way of proceeding towards finding these changes in strain energy. Why? Because we are familiar with ways of calculating the work done in various kinds of systems. Now, it is very much possible without appealing or without taking up individual, special cases to express or to find an expression for this delta U or the change in the strain energy by starting with something like this, okay? That you take the W and you consider a body force like this, multiply that by the displacement integrate over the entire volume, and you take the traction, multiply that with the displacement, calculate it over the entire surface, and then you do some special algebra with this. I mean, there's nothing special. You just have to know a few extra things. Okay, so if you proceed like that, you will end up with a very general expression for the delta U. We are not going to do that. Okay, we're not going to do that because at the second year level, you don't need to understand all that general things. Plus, showing you that derivation will be unnecessarily taxing you on things which you don't need at this moment. All right. So what we are going to do is we are going to take a very standard textbook kind of approach. Standard textbook approach is that we take simple cases, like the kinds of cases which we will be actually concerned with when we start to do the problems, and it is only in the context of those cases that we find the expressions of the strain energy. Mind you, of course, that this is not the most general thing you are going to discuss. We are going to discuss these ideas only as a means of solving our problems. Okay. So what do we do? So we'll take the simplest of cases for the work done. Simplest of cases means, let me just write this, consider simple cases. So first of all, consider a bar like this, which is subjected to axial loads like this. Okay, now this axial load is not exerted outright like P. Rather, we gradually increase the force from 0 to P. And when we do that, we want to find out what is the resultant change in the strain energy of this rather simple, straightforward mechanical system, which is just a simple rod. Okay, so how do we express this thing? How do we express the work done associated with it? Can we not write something like this? Where this delta, the upper limit of integration for this x, this delta is the final change in the length of this rod. Okay, the ultimate change in the length of this rod, that is given by this delta. What is this f? Well, this is the part where we have to appeal or where we have to utilize the intrinsic material behavior of which this rod is made. What I mean by that is that, so these are the kind of things which you may not have been told explicitly back in +2. Okay, now I have to tell you explicitly because you do have the proper background to understand this. We can proceed with the calculation of the expression by assuming that the relationship between the applied force and the deformation is linear. Okay, so assume, and this is a very big assumption. Okay, so assume that force is linearly related to the deformation. So exactly the kind of situations, the kind of situation which you are familiar with in the context of a linear spring. Okay, same kind of idea, that the force is linearly related to the deformation. If that is so, then we can easily say that F is equal to P times X by delta. Why this makes sense? Because when X is 0, our force is 0. When X is equal to delta, our force is equal to P, which is exactly the kind of situation I have described in setting up my problem, that the force is being gradually increased from 0 to this value P. And if we substitute this expression here, what we are going to obtain is this Px by delta dx, 0 to delta. And if I just go to the next page quickly, this W is going to end up as P by delta square by 2. So this becomes half of P into delta. So it is as if, so this half of P, it is like the average force that is being applied on this rod. Okay, this half of P is the average force that is being applied on this rod. That average force times the total increment in the length of the rod, that is the total work done. Okay, and this is going to be equal to the change in the strain energy, and that follows from our simplified version of the first law of thermodynamics. Okay, so based on this idea, we are next going to discuss how to determine the change in the strain energy associated with situations where you have to deal with the normal stresses, where you have to deal with the shear stresses. And once we have done that, the normal stresses and the shear stresses, we'll be in a perfect position to find out the various kinds of common mechanical situations, mechanics of solid situations we have been dealing with in our previous chapters. All right, we'll continue with that in the next class. Thank you very much.
Thank you, sir.
Thank you, sir.